Alright, let's see what we can do with the rest of the mass spec fragmentations. We are going to push electrons like there's no tomorrow in this mini lecture, so be prepared. Alright, so just a quick recap to begin. We're going to throw our sample into the mass spec. Electron's going to be lost. For us to have any kind of rational chance at predicting either what to expect in the mass spectrum or to analyze and understand the mass spectrum, we need to propose a structure for the molecular ion. Where is the odd electron located? So once we've done that, then we can push electrons, and that's our goal, to understand how this thing is going to logically, rationally fall apart. In general, the most stable fragment will be the one that's the base peak, and that most stable fragment is, following the same rules that we've seen all along. Radical cation that's tertiary is going to be more stable than secondary and primary. That said, as we've already suggested, there's definitely going to be times when we have primary radicals and primary cations. Those fragments won't be as abundant. So keep that in mind. This is what's going to allow us to see the larger, more abundant peaks. Another important thing to think about is, as always, resonance, because of course resonance helps stabilize things. And we've seen that in the previous mini lecture with the tropylium ion. So yeah, we've looked at alkanes, aromatics, alkynes. Now we're going to look at heteroatoms. Heteroatoms meaning anything that's not a carbon. Heteroatoms meaning things like halides, oxygen, nitrogen, sulfur, anything with lone pairs. So amines, ethers, alcohols, you name it. The key fragmentation pattern that we're going to see in the mass spec for samples that contain heteroatoms is something called alpha cleavage. So we'll start by looking at diethylamine. Diethylamine, being an amine with one nitrogen in it, has an odd molecular weight. Its molecular weight is 73. When we hit it with 70 electron volts in the mass spec, lose an electron, we get this proposed molecular ion, which of course has the same mass. Now it's our mass to charge ratio. So there's our molecular ion. What's going to happen next? Well, alpha cleavage. So what is alpha cleavage? Basically what we're saying is that you start by putting your arrow on the odd electron, and it would like to pair up with somebody again. And so right next door, right here in the alpha position, it's going to homolytically cleave that bond between the alpha and beta carbons. So these two red arrows are saying, we're going to link up and make a new bond. And this green arrow is saying, I'm going to spit out a methyl radical. So the result of this alpha cleavage is that I end up with this charged fragment, which is detected, and this methyl radical, which is not detected. So this should be a pretty predominant peak, especially since my alpha cleavage could take place on the other side as well, and would give me the exact same charged particle, charged fragment. So what would I expect to see? Well, C3H5, 6, 7, 8, N, whatever that adds up to, so 36, 43 plus 14, 57. I would expect to see a fairly abundant peak for the fragment ion that has this structure at mass to charge 57. What about alcohols? Alcohols, same kind of structure for the molecular ion. We pluck out an electron off the lone pair on the oxygen. But alcohols have another feature that's very interesting. It's very easy for them to be dehydrated in the mass spectrometer. And because of that, since they lose water just like that, it's not unusual for you to not have a molecular ion for an alcohol. So that can be very confusing. Otherwise, you can look for the M-18 fragment ion. How in the world does that happen? Well, we'll show you with 2-heptanol. So basically, if you're looking at 2-heptanol here, what you want to focus in on is the fact that you can bend the molecule around on itself and have that nifty 6-membered ring transition state. That's super stable. It's really easy for my radical, my unpaired electron there, to reach over here and pluck off that hydrogen. Easy peasy. Once that happens, what do I get? Well, all I've done is I've transferred the radical, the unpaired electron, to this carbon, but more importantly, what you can see is I now have a fantastic leaving group. So, as you might expect, that's going to be gone in a heartbeat to give me this radical cation. So I still have a radical, I still have a charge, so this will show up in the mass spec. This won't, because it falls apart too quickly. But it turns out that even this fragment at mass to charge 98 falls apart pretty quickly, because neutral molecules, neutral stable molecules that look like this alkene, wow, that's super stable. I mean, it's not a radical, it's not a cation, it's just a normal molecule. So that last fragmentation also takes place really readily. And so what I see, I may see a little bit of a fragment ion at 98, but I should see a more substantial fragment ion at 56. Again, this is going to be what's detected because of the charge. Well, what about it? Do we see that? Here's the mass spectrum of 2-heptanol, and what we see is there's our fragment ion at 56, and there is our, if you look really hard, you can barely see 1 pixel's worth of a molecular ion there. That's not good for anything. But strangely enough, the base peak is this thing at mass to charge 45. Now, we can't always come up with a reasonable mechanism for, we ignore almost all of these little tiny peaks. Who knows what they are and who cares? But this base peak, we ought to be able to come up with something. Well, what I can tell you makes sense is that it has this structure, that this is a really stable carbocation, stabilized because of resonance, and this has the right molecular weight to match the mass to charge of 45. How is it formed? I don't know. Maybe that's something you can play with. So, that's an alcohol for you. Now, what about carbonyls? Carbonyls also undergo alpha cleavage quite readily, but if they're big enough, they also undergo something called the McLafferty rearrangement. So, we'll look at 2-octanone as an example. And as you would predict, we have knocked off an electron from the lone pair on the oxygen as our molecular ion starting point. That said, what's this going to do? Well, alpha cleavage says it's going to go right here and homolytically cleave the bond between those 2 carbons. Okay? Well, fine and dandy, but what about going this way? Well, I don't really have room there. Let's try again. We're going to put that there and put that there. Is that feasible? Well, absolutely. We can have alpha cleavage on either side. And in fact, one route kicks out the methyl radical, so M-15. The other one kicks out the 1, 2, 3, 4, 5, 6 hexyl radical. We don't necessarily care about the molecular weight of the hexyl radical, but what we do care about is looking at where the expected fragment ions would show up. And so what we see is that this longer chain fragment ion would show up at around 101, and this little dinky one shows up at about 43. So alpha cleavage, quite feasible, quite prominent. But what about this McLafferty rearrangement? This one's super cool. It again has to do with the six-membered ring transition state. So I think the take-home message here is that if your radical cation, or your odd electron, can pluck off, do a hydrogen abstraction from a hydrogen 6 atoms away, that's going to happen in a heartbeat. And that's just a terrible job showing that happening. Let's try that again. Here we go. Plucking off that hydrogen and putting the odd electron on that carbon. So that's the mechanism. That's the electron pushing. What we've essentially done is protonated our carbonyl and put the radical right there on that carbon. What happens next? Well, what happens next is that it's off to the races. These things love to fall apart to give stable, neutral molecules. So if that cleaves as shown, what I will end up with is another alkene that is happy as can be. It's a normal molecule. It's not a cation, it's not a radical. Since it's neutral, it's not detected, and I've lost a piece of my molecule that weighs 70 mass units. But more importantly, what I see is the charged fragment. I should expect to see a significant peak in mass to charge 58, and indeed you do. So that is a whole slew of mass spec fragmentation mechanisms for you. Take-home message is, for mass spec, you use it as confirmatory information. So either you know what your molecule is, or at least you have a strong suspicion, and you use the mass spectrum to confirm it by confirming the molecular weight and reasonable fragmentation patterns, reasonable fragments that show up in the mass spec. Very rarely do we look at a mass spec without having any idea what our molecule is and get useful structural information from the mass spec all by itself. It's used in conjunction with NMR and IR. Sure, if you have a M-15, you know you've got a methyl group in there. You can use those common fragments lost. You can lose those structures of those common fragment ions. But generally speaking, mass spec is best for confirming a structure that you already suspect. All right, so what does rho, rho, rho have to do with this? Well, of course, it's a bad joke. And that is thinking about these poor slaves and prisoners in, these horrible galleys that have to row and row and row under chains because, they're prisoners. So one day the captain of this boat, the royal barge, went down to address these slaves chained to the oars. And he said, "Men, the good news is that the Queen will be joining us today for a trip up the river. The bad news is she wants to go water skiing." Yeah, that one's a stretch. All right, well, we'll have fun doing mass spec mechanisms in class. See you then.